This screencast is about buffer calculations, specifically the addition of small amounts of acid or alkali to buffers. So make sure before you move on with this one that you are quite clear on how we calculate the pH of buffers that are made from a weak acid and its salt. If you need some help with this at any point, then you can find chapter 8 of the Jim Clark calculations book. There are loads of worked examples, and obviously there are answers in the back for the exercises, so that is a really good place for you to practice and get good at this. So a quick recap on what's happening when buffer action is occurring. So when we add acid or alkali to a buffer, then we get some equilibrium shifts, and you need to be able to write about those qualitatively. So you need to be able to say that they're happening. But there's also a reaction with a large excess of something within the buffer solution, and this is the bit that's used in calculation. So our large excess in there is, we've got a lot of the acid HX and we've got a lot of the salt X minus. Okay, so both of these things we've got large excess of within the buffer solution. So let's have a think about what would happen if we add H plus. So in terms of what will happen with the large excess of substances that are there in that buffer, the H plus will react with the large excess of X minus, leading to an increase in the concentration of HX and a decrease in the concentration of X minus. So these are the two bits that you would adjust in your calculation. So you'd have a new HX and you'd have a new X minus when you were doing this calculation. I'll show you how to do it in a minute. And with the OH minus, they react with a large excess of the undissociated acid HX. That leads to an increase in the concentration of X minus, because the OH minus is only taking the H from the HX, and then it ends up with a decrease in the concentration of HX. So you've got new numbers to put in there as well. Just going to remind you that OH minus will take the H from HX, leaving X minus on its own, just in case that's not obvious to you. So let's work through some calculations involving an acidic buffer. There's a scenario at the top there. Now you'll notice that it's just moles. I haven't given you concentrations, haven't given you volumes or grams or anything like that. So this is the simplest form that we can look at. So you've been given a moles of HX, you've been given a moles of the X minus, and you've been given a Ka. And there's three parts to the calculation. To calculate the pH of the buffer to start with, which is number one. Number two, to calculate the pH after you've added a small amount of acid. And number three, to calculate the pH after you've added a small amount of alkali. Now remember that we are using the expression Ka is equal to concentration of H plus times concentration of X minus over concentration of HX. Now it doesn't matter if they're not concentrations as long as they're the same thing, because remember, when we are rearranging this, we end up with concentration of H plus is equal to Ka, oh, wait a minute, I've written the wrong symbol there. That should be times concentration of HX over concentration of X minus. So you don't need to convert to concentration or anything like that for this. It's this form that you're going to use to get the moles of H plus and the concentration of H plus and be able to work out what the pH is. So the first calculation, I've put at the top the bits of information that we needed, which is the moles of HX and the moles of X minus and the Ka. And I'll just remind you of the rearranged formula that we're using. Okay, So we're going to plug just need to plug the numbers in here. So 1.81 times 10 to the minus 5 times 0.4 over 0.25. So this comes out at 2.896 times 10 to the minus 5 for concentration of H+, and therefore we're going to work out the pH. We're just going to stick that into minus log, and that gives us a pH of 4.53. Remember, 2 decimal places for all your pH quotes, please. So now we're going to consider what happens to the buffer when we have added some H+. Let's remind ourselves of the values we had before. We had 0.4 of HX, we had 0.25 of NaX, and we had a Ka of 1.81 times 10 to the minus 5. Okay, so I have to figure out what's happened here, because when we add the H+, it is going to react with the X minus to give HX. So X minus concentration is going to go down, and HX concentration is going to go up. So now we're determining what the new amounts are of these things. So let's deal with our X minus first. So new X minus is equal to 0.25 take away the 5 times 10 to the minus 3. So we're going to end up with 0.245 for that. Then our new concentration of HX, we're going to add it on. So in all of these calculations, you're going to have one that goes up and one that goes down, because obviously it's an equilibrium. So that's going to give us 0.405. So plugging this into the calculation as we did before, concentration of H plus is equal to Ka times HX over X minus. So 1.81 times 10 to the minus 5 times 0.405 over 0.245. So that gives us an answer for H plus of 2.99 times 10 to the minus 5, and therefore I'm going to do the pH of that, just minus log again, and that gives us 4.52. That seems a sensible number. Our previous number was 4.53, but we've added H+, so obviously it's become more acidic, so a lower pH should make sense. So now on to version 3, what happens when we add OH minus to this? So again, we need to think what's happening. So the OH minus is going to react with the HA. It's going to take its proton to make H2O. Sorry, it's not HA, it's HX. There we go. HX. It's going to take its proton to make H2O and X minus. So that means that the concentration of HX is going down and the concentration of X minus is going up. So let's have a look. We're going to go for a new HX. What's our new amount or moles of HX? So 0.4 take away the 5 times 10 to the minus 3. Leaves us with 0.395. Now we need a new X minus, 0.25, and we're adding on the 5 times 10 to the minus 3, with 0.255. So we're going to plug it in to our calculation. So we're going to do Ka times HX over X minus, 1.81 times 10 to the minus 5 times 0.395 over 0.255. So our answer to that is going to be 2.80 times 10 to the minus 5. And we're going to do the pH of that, it's just minus log. That comes out as 4.55. 2 decimal places, of course. So let's just quickly compare the pHs in what we just did, just to make sure that they're sensible. So our original buffer was 4.53. And when we added H+, we ended up with a number which was 4.52. And when we added OH minus, we got 4.55. So you can see that isn't a very big change in pH. You do have the mental check, is this a sensible number? So adding H+, you'd expect the value to go down because it becomes more acidic, so tends towards the lower end. And you'd expect it to go up with OH-, so those numbers that we've just got make sense. And you also wouldn't expect in these calculations to get a number that's very far away from your original value. So if one of these had come out at like 4.7, then you've done something wrong. You will usually be within the kind of second decimal place in terms of orders of magnitude with these. So here are a few for you to try. The first buffer recipe is very similar to the one that I've just done for you. In the second one, you'll notice that you've got volumes and concentration, so you'll have to deal with those first before you start plugging them in. And also you've been given pKa instead of Ka. So remember, pKa is just minus log to the base 10 of Ka, so you can just convert that back before you start tackling the calculation. So pause this now and have a go at it. I will put the answers on the next slide, but do pause it and have a go yourself before you look at me doing it. Okay, I hope that you paused that and had a good go at this yourself to make sure that you can do it. So question 1, the answer to the pH of that recipe is 4.69. And for part B, which is the addition of the H+, it goes to 4.67. And for part C, the addition of the OH-, it goes to 4.69. So that's exactly the same way as we did the first example. Just check your answers and make sure that they're right. You might be the odd second decimal point off depending on rounding errors. Don't worry too much about that as long as you're in the ballpark figure. So question 2 was the more difficult one. There were some bits that you needed to do at the start. So just to make sure that you got these right, and in case it's a source of any error, you'll end up with a Ka something like 1.778 times 10 to the minus 4. The original moles of acid should be 0.015, and the original moles of salt should be 0.045. So just in case those aren't right for you to start with. So then the answers, 4.23 for the original buffer solution. If we add acid, it goes to 4.05. And if we add alkali, it goes to 4.45. So you can see this, there is actually quite a bit of difference between these numbers. It's probably because we're getting the buffer to the limit of where it's able to buffer to, really. It's not a huge difference. What about 0.2, isn't it? But it's getting towards the limits of what we would consider buffer action. And in reality, that's just because I made the numbers up rather than choosing a kind of definite system. So just check your answers for that. Make sure that you understand it. Upload your working out to this onto Showbie for me so that I can see that you've understood it, and I will send you some more questions on this on Showbie as well.